desk different types of inhibition, and especially two types which you have to write in your experimental books. There are lots of different neuronal nets where we will find which are having these inhibitory connections, and many neural nets where we may find inhibition types of interaction, inhibitory types of interaction between the neurons. So, primarily to know is that there are many excitations in the brain. They are interacting with each other, and sometimes we may find, after the interaction of two excitations, we will find intensifying of main excitation, of main behavior. For example, if the cat is eating, it's displaying feeding behavior, and you slightly, but very slightly, sub-threshold, you should apply some mechanical influence on its tail, for example, or its skin. But it's important to know that it should be non-dominant, sub-threshold stimulation of skin, of tail receptors, mechanical receptors, of its sensory analyzer. Then you may see which changes of dominant behavior you will find. You will apply second excitation, second afferent input, sensory input into the brain, and you will see how would change its activity, main behavior, main activity. This cat would eat with in more aggressive way, more fast, more aggressive way, because second excitation would be interacting somehow with the main excitation of feeding behavior in the brain, and you will see intensification in that case of main behavior. That's the example which is opposite to inhibition. Today you write in your books the experiment of cessation of inhibition, where we have second, let's speak first about the Goltz inhibition, which is second in your practical book. That's linked inhibition of Goltz. So, linked inhibition. You apply second activation, not on the stimulation of skin, but you apply second stimulation, second excitation with mechanical stimulation of skin of contralateral leg. So you check on the one side of the body the time of the reflex of Turk's time with acid application on the skin, and simultaneously, first time you determine this time, you measure this time. Then, simultaneously with next acid application, you press another leg. You apply mechanical stimulation on another leg. Also, and then simultaneously you apply the acid. You see also interaction of two excitations in the brain, in the spinal cord especially in this experiment. Now we told about the example where we observed intensification of the main behavior. In this example you observe opposite situation. In this example you see that if you press mechanically another leg, you will see increase in time reaction, in its reaction with acid application. So the time of the reflex, the Turk's time, will be increased. So you see not the intensification of this reflex, but its inhibition, its suppression. The time of the reflex will be increased. So opposite example. The same, we may find many other situations which somewhere we will see intensification of the main behavior, but in some other cases we will see the inhibition of the main behavior. So why we see here in this example inhibition, and in other case, in the interaction of two excitations, we see the intensification. So what's the reason for the inhibition in one example and intensification in the other? Last lesson you checked the reflexes, tendon reflexes, and we told that if the reflexes are low, we may apply some special manipulation. We tell to the patient to take his arms and to pull to different sides, and under this effort in motor neurons of the arms in spinal cord, we observe intensification of the reflexes. So So what's the reason for this? That's another example of interaction of two excitations. We make one excitation in the motor neurons of thoracical segments of spinal cord, where the arms, reflex arms of reflexes of the arms passes through the spinal cord. And this activation of motor neurons of thoracical segments interacting somehow with lumbar segments of spinal cord, where we have the reflex arms of the legs, where we check the reflex. So we have also this example of intensification. So what's the reason for the intensification or inhibition in other example of limb inhibition? Why we see inhibition in linked example of Gord's inhibition, and why we see intensification of reflex in other examples? So what's the reason for the inhibition or the intensification? Спасибо, что тестировал. So what's the mechanism of this intensification if we pull the arms and check tendon reflexes? Which mechanism of interaction of excitations we may use to explain this type of intensification of the main process by the non-important second excitation, non-dominant. So we make here non-dominant excitation in the motor neurons of the thoracical segments of the arms by arms movement. And this non-dominant excitation interacts somehow with lumbar, with this reflex, main reflex arc, which we check by reflex. So what's the type of their interaction? How do they interacting? Which types of excitation propagation in the CNS we may use to explain their interaction? Because thoracical segments are in the upper part of spinal cord, lumbar segments lower, below them. They're in different places. How they are interacting? Due to which mechanism of propagation? We spoke here last lesson about different types of excitation propagation in CNS, and one of this type may explain how they interact with each other. So which type of propagation of excitation in CNS may explain us the way of their interaction?
Autonomy.
Huh?
Autonomy.
Autonomy? No. Not autonomy. You see, here is thoracical, cervical, thoracical segments. And here we have spinal reflex arc with the muscles of the arms. Here we check in lumbar segments tendon reflex from legs. They are in different parts of the spinal cord. How excitation in this reflex arc, voluntary movement from precentral gyrus, decreasing and inducing the activity of motor neurons of the arms. We give this command by our cortex to pull the arms, voluntary movement, and how this activation of motor neurons of arms may influence motor neurons of the legs in lumbar segments. Which type of excitation propagation in CNS may explain us this interaction? Irradiation. Irradiation of excitation. That's first explanation. Irradiation. This excitation irradiates, goes to different other places. That's irradiation. Do you remember such type of excitation propagation? No? Yes? No? Okay, then you should study the previous lesson better. Because on the prologue we will discuss all these types of interactions. That's irradiation. First, it's irradiating down and up. That's the irradiation of excitation first. Then, this non-specific activation, this non-specific excitation, passing through these synapses. Second type of interaction in synapse. If in synapse first excitation goes through, it it depolarizes postsynaptic membrane partially and makes more easy passage of the second depolarization. So that's synaptic plasticity. That's second property of synaptic transmission, which explains this type of interaction, this type of intensification. So that's synaptic plasticity, that's synaptic propagation. With the for the second depolarization, it's more easy to go through the synapse if there was first synaptic excitation. Fast. So that's the second type of synaptic interaction, second type of property of synapses, which explains us why, in the case of two excitations interaction in the CNS, sometimes we observe intensification of the main activity. So that's the explanation: irradiation and synaptic plasticity. These two properties underlie this type of interaction, which we may find in many cases in the body, in the brain, where one excitation intensifies the other. We may find other examples if you, for example, getting tired, but you should sleep or read some information, concentrate your attention. It's difficult when you're tired. It may be more easy to do this concentration, to study, if you, for example, hearing some low music, or if you have more bright light. Because our external receptors, eyes or sound receptors, hearing, become activated. This non-specific activation coming into the brain intensifies our brain function centers, which are involved in this main studying process. So in some cases, if this music is low, of low intensity, or if this music not turns our attention to its sound, to the songs and so on, but if this music becomes non-dominant, then it intensifies our brain activity. So that's the example of opposite meaning to inhibition. And now other examples of inhibitory interaction, when one excitation born come into the CNS may inhibit main activity. That's opposite way. So we take spinal cord, this reflex arc receptors will stimulate with acid, and simultaneously the other contralateral leg will stimulate mechanically. That's Gold's inhibition, written in your book, which you should now write the experiment. So, what's their interaction? We have two excitations simultaneous. And we will see in this example, special example, opposite way of interaction. This second excitation will not be intensifying the time of the reflex, this reflex which we measure the time. It will inhibit, it will increase the time of this reflex. Before the mechanical, the probe will take its own leg from the acid in 2 seconds, for example, but after application of the contralateral mechanical stimulation, this time of the reflex would increase up to 10 seconds. 10 seconds this leg would stay in the acid before it would be taken from the acid. So that's caused by another excitation. That's opposite way of interaction than we spoke before. That's inhibition. So why? In this case, there would be inhibitory interaction between two excitations. So how we can explain this? In any case of inhibition, in any example of inhibition, we have special activation, we have special excitation which inhibit the other. And how that may be done? That in one case, in one example, it will be intensifying, in the other it will be inhibiting. If in first example it causes partial depolarization, that's synaptic plasticity, yeah? Partial depolarization of the membrane postsynaptic. The threshold and this partial depolarization by the first excitation through the synapse, it causes partial depolarization and thus increasing excitability, right? So that's partial depolarization caused in the first example when we had intensification of main process, right? Here is partial depolarization. But if we speaking about the inhibition, we will find on postsynaptic membrane the other example, the hyperpolarization. And hyperpolarization decreases excitability of postsynaptic main neuron. So that's the example of inhibition. And you remember, I hope, that this inhibitor, IPSP, and here,
EPSP.
this EPSP. So, we should include in the neuronal net of interaction, in the case of inhibition, we should include, integrate inside this neural nets special neuron, which will secrete the other mediator, which will not depolarize but hyperpolarize the membrane. And this mediator is two types of inhibitor mediators, GABA or glycine. And we should include, integrate into the neural connection such neuron, inhibitory neuron. And that's only the reason. We have collateral, which will excite simultaneously with this neuron would be excited, this neuron would be excited on the reflex arc, excitation, and this neuron would excite this neuron, and as well as this collateral would excite target neuron of this synapse, and this would be inhibitory neuron. This neuron of red pants, of red color, is secreting GABA or glycine in this synapse, thus hyperpolarizing this target neuron. And this target neuron would be hyperpolarized. There will be, on the postsynaptic membrane, on this neuron, we will find hyperpolarization, and it would be more difficult to excite this neuron. So we need more time of impulsation, more intensive stimulation of these receptors to find to observe the reflex. So in each nets, in each type of inhibition, we always should allow, we always will find inhibitory excitation activating, that's depolarization of, that's activation of this inhibitory neuron. This inhibitory neuron becomes active, it excites and secretes special the other mediators, GABA, which is hyperpolarizing main neuron, which is giving us some activity. So that's general way of inhibition. And now you will read about the Sechenov type of inhibition. Later inhibition, you should be able to draw to show how neurons are connected with each other in later inhibition and many other types of inhibition. So now, in the same way, analyze and write the experiment with Sechenov inhibition. Sechenov inhibition, in this type of inhibition, in Sechenov inhibition, in thalamic, we induce second excitation by direct stimulation of thalamus. We apply sodium on the thalamus, it induces its activation of thalamus, and spinal thalamic pathway takes this excitation down throughout the spinal cord, and that's the anatomical connections, that this downstreaming excitation through spinal thalamic pathway, it activates cells inhibitory interneurons. So spinal thalamic pathway, which goes down, streams down through the spinal cord, it activates not directly motor neurons, but it activates interneurons, inhibitory interneurons. That's anatomical construction of the spinal cord. Thus, by activation of thalamic nucleus with sodium, with salt application, we induce activation of Renshaw of these inhibitory cells in spinal cord segment. Thus, they hyperpolarize motor neurons and we observe increase in time of the reflex. So that's Sechenov inhibition. The same type, but we under Sechenov inhibition induce another activation, not by mechanical applications here, but by salt application of thalamus. That's another way to induce other activation. So that's your task now, to write the experiment and analyze other types of inhibition, which you know from books and from lectures. So now start writing the experiment.
5.2.
5.2 and 5.1, I suppose. Section of 5.1 and points 5.2, yes. Yes. That's next lesson.